Alright, we are going to continue talking about zeros of polynomial functions. And here we go. Alright, the rational zero theorem. What the rational zero theorem says is if you have a polynomial, okay, and what you're interested in is this leading coefficient and this constant at the end. If this polynomial has integer coefficients and p over q is a rational zero of f, then p has to be a factor of a sub naught, and q has to be a factor of a sub n, the leading coefficient. So your possible rational zeros are all the factors of the constant term over all the factors of the leading coefficient. This was a huge theorem back in its day. When you take a polynomial function and you're asked to solve it, what you're asked to find is where the thing crosses the x-axis at, okay? These polynomial functions, you know, are smooth, continuous curves, okay? This one that I just drew has 3 zeros, obviously. Well, what some guy figured out was whenever you're looking for these zeros, I mean, when you're just, if somebody just gives you a random polynomial, the answer could be anything. Well, back in the day, you had to check every number from negative infinity to infinity to figure out if it crossed the x-axis there. Well, somebody came up with the rational zero theorem that said, and noticed every time that it crossed at a rational number. Now, it's got to be rational. You know how sometimes we end up with answers like 2 plus or minus the square root of 7 over 5 or whatever? That's a real number. It's going to cross the x-axis, but that's not a rational number because of this square root in it. So it doesn't help us find these kinds of answers, but if it crosses at a rational number, the guys figured out, or whoever figured this out, figured out that if it crossed at a rational number, that rational number always had, the top was a factor of the constant, and the numerator was always a factor of the leading coefficient. So it meant we didn't have to check every number in the universe. It took our possibilities from an infinite amount of possibilities down to a manageable amount. Okay? So, it says list all the possible rational zeros of this function. Alright, my a sub naught, my constant, is 4. My leading coefficient is negative 1. Okay, everybody with me? There's my a sub naught. My a sub n, my leading coefficient, is whatever's touching the highest degree. So in this case, it's negative 1. Okay? Now, all I have to do is figure out all my factors of a sub naught. The only numbers that go into 4 are 1, 4, 2, and 2. The only factors of negative 1, and I don't really need the negative, the only factors of 1 are 1 and 1. Now, this is where my p's are. These are my possible p's. And these are my possible q's. So to make my possible PQ list, all you do is you're going to start with the first P, and you're going to put it over every Q. So I have this one over this one. So 1 over 1, and then I move to the next one. My next P is 4. So I put it over Q. And that gives me 4 over 1. My next P is 2. So I put that over 1. I get 2 over 1. Now I clean it up and I add my plus or minuses. Plus or minus 1 divided by 1 is 1. Plus or minus 4 divided by 1 is 4. Plus or minus 2 divided by 1 is 2. My possible PQs, in other words, if this thing crosses at a rational number, it's going to cross at either plus or minus 1, positive 1, or negative 1. Sorry, I don't want you to see that picture yet. It's either going to cross at, if it does, doesn't mean it will, but if it has a rational zero, it'll be at positive 1 or negative 1, positive 4 or negative 4, positive 2 or negative 2. We'll worry about finding them in a minute. I just think it's important that you see, if I graph this, there it crosses at negative 2, and there it crosses at positive 2. This thing can only have at most, this thing will either cross the axis 4 times or less than that by 2. So or 2 or 0. And you can see that this thing crossed twice Okay, and those are the two rational zeros, which means the other two must be imaginary. All right, so list all the possible rational zeros of this function. Well, my a sub naught is -2. My a sub n is 15. My factors of 2 are 1 and 2. Factors of 15, 1 and 15, 3 and 5. So these have to be my possible p's. These are my possible q's. So my possible PQ list, I'm going to take my first P and put it over each one of my possible Q's. So I have 1 over 1, 1 over 15, 1 over 3, 1 over 5. Then I'm going to take my next P, possible P, and I'm going to put it over each one of these. So I have 2 over 1, 2 over 15, 2 over 3, 2 over 5. And those are my possible P's. I'm going to clean it up. So I have plus or minus 1, plus or minus 1/15, plus or minus 1/3, plus or minus 1/5, plus or minus 2, plus or minus 2/15, plus or minus 2/3, plus or minus 2/5. Those are all of my possibles. Now this thing, again, this thing could cross 3 times or 1 time. Okay? It could cross 3 or 1 time. If it crosses 3 times and they're rational, it will be at one of these numbers. Okay? And again, we'll worry about actually finding them later, but for right now, I do want you to look. And if you look, there's my -1, which is in my list. Okay? So -1 is a 0. This one is -0.33333333 repeating, which if you type that in a calculator is 1/3. There's my -1/3. And then the third one is at 0.4. And if you change 0.4 to a fraction, that's my 2/5, which is over here. So it did cross 3 times, and the 3 rational zeros are in the list. And I know you're going, that's a lot of possibilities. Yeah, but it's a lot less than infinity. Alright, so you go find your possible PQs, hit pause, come back when you're ready. And hopefully you got 3. So my a sub naught is 12, negative. My a sub n is 1. Factors of 12, 1, 12, 2, 6, 3, 4. Factors of 1 are 1. So you have 1 over 1, 12 over 1, 2 over 1, 6 over 1, 3 over 1, 4 over 1. You gotta love it when your leading coefficient is 1. That doesn't make many fractions, okay? So my list is plus or minus 1, plus or minus 12, plus or minus 2, plus or minus 6, plus or minus 3, plus or minus 4. In what order you go in does not matter. Alright, and again, if I look, the interesting thing here, again, you're not supposed to worry about this yet. I'm just kind of showing you what happens. If I type this in my graphing calculator, and I'll show you how to calculate these zeros if you don't remember. If I calculate this, I get -4.643754 and 1.620167. And if I try to turn those back into fractions, which is what rational means, the calculator won't do it. What that tells me is that this function has no rational zeros. You can see it does not cross at +1 or -1. It does not cross at +12 or -12. It does not cross at +2 or -2. +6 or -6, +3 or -3, +4 or -4. It doesn't cross at any of these, which means this function obviously, again, this thing could cross 4 times or 2 times or no times. And you can see it crossed twice. It has 2 real solutions, but they're not rational because they're not in this list. And you can't make them turn into fractions. Alright, go. Hit pause, come back when you're ready, and hopefully you got 4. My a sub naught is 2, My leading coefficient is 7. Factors of 2 are 1 and 2. Factors of 7 are 1 and 7. So 1 over 1, 1 over 7, 2 over 1, 2 over 7. Add your plus or minuses, plus or minus 1, plus or minus 1/7, plus or minus 2, plus or minus 2/7. Those are all the possibilities. And I can look, and it crosses, again, this thing is a third degree, so it could cross 3 or once. This thing crosses once. And if I tried to make that a fraction, I can't. So it has a real 0, but it's not rational. Alright, so explain how to use the rational zero theorem to find all possible rational roots of the polynomial. Your p is a factor, your possible p's. Your possible p's is factors of a sub naught. Your possible q's is a factor of a sub n. And your possibilities are all of your p's over your q's. Alright, so finding zeros. Now we're going to talk about how to find them. What you do is you're going to list all your possible rational zeros. And then you're supposed to test each one until you find one. That can get tedious. And believe me, back in the day, this theorem was awesome. But with the technology we have today, we're going to kind of cheat a little bit. We're going to go ahead and make our list, but then we're going to use the graphing calculator, and we're going to see which ones from the list are zeros. It's just going to save us some time from doing a lot of testing of zeros to find out that they don't work. Once we find one, okay, if we divide by it, that will depress our polynomial down. And we keep doing that until we depress it to a second degree, and then we can use our quadratic techniques to find the remaining zeros. So it says find all the zeros of this function. Well, I have no idea. Okay, we can't factor this because it's a third degree. We could try 2 by 2, but it ain't going to work. So my normal techniques of finding zeros isn't going to work. So that's why we use our PQ list. Well, my a sub naught is 6. I know it's negative. All the factors of 6 are 1, 6, 2, and 3. My leading coefficient is 1. All the factors of 1 are 1. So my possible PQs are 1 over 1, 6 over 1, 2 over 1, 3 over 1. Clean it up. My possible rational zeros are plus or minus 1, plus or minus 6, plus or minus 2, plus or minus 3. Now, what we would have to do in the olden days is you would just start. You would just put 1 in the hole and see if you could divide by it. Third degree coefficient, second degree, first degree, constant. 1 comes out, brings back 1, comes out 3, brings back 3, comes out negative 2, brings back negative 2, comes out negative 8. That's my remainder. So positive 1 is not a 0. And then I'd have to try negative 1. 1, 2, negative 5, negative 6. 1 comes out, brings back negative 1, comes out 1, brings back negative 1, comes out negative 6, brings back... I found one because my remainder is 0. So again, I'm looking for 3 of them. I found 1. Now, this can get pretty tedious, especially when you get a lot of fractions and so on and so forth. So what I'm going to do is, and what I'll let you do, is once you get your list, then we're going to go to the graphing calculator and we're going to type it in. And I can tell from my graph that it crossed at negative 3. Okay, I can also see that it crossed at negative 1, which I just found here. And I can also see that it crosses at 2. Now, that would be completely cheating. So what we're going to do is pretend that we're just going to use it to find 1. The reason is, if it's a third degree, I have to find 1 from the list or the picture. Because if I can find 1, I can divide by it, which will drop it down to a second degree. Now, if this was a 5th degree, I would have to find 3 from my list or my picture to get it down to a second degree. Okay, I hope that makes sense. All right, so I'm going to do this. So pretend I didn't do any of this. Okay, I mean, that's the way you would have to do it in the olden days. You would just have to check each one by hand. So I'm going to make my list. I'm going to go to the calculator. I'm going to find 1, and it does not matter which one you find. This shows me that negative 3 is a 0. So if I put negative 3 in the hole, my polynomial coefficients, third degree coefficient, second degree coefficient, first degree coefficient, constant. 1 comes out, multiplies by negative 3, brings back negative 3, comes out negative 1, goes to get negative 3, brings back positive 3. Negative 5 eats positive 3, comes out positive 2. Positive 2 times negative 3 is negative 6. What the heck just happened? 1, negative 3, negative 1, positive 3. Oh, that comes out negative 2, sorry. Which comes back positive 6, which gives me a remainder of 0. Now, what's neat about this is, just like we did before, you have to press the polynomial. My original function was a third degree, so this is now a second degree. And now that I have a second degree, I can find the remaining zeros by factoring this. This should factor. Factors of 2 that make 1 are 1 and 2. C is negative, so only the bully gets the middle, and 1 will be positive. And if I set those to 0, x minus 2 equals 0, x plus 1 equals 0, add 2, x equals 2, minus 1, x equals negative 1. And I already had this one. There has to be 3 solutions. They're not necessarily all rational. In this case, they were. My 3 solutions are negative 3, 2, and negative 1, which you can see on the graph. And these were all in the list. So all of its zeros happen to be rational. Doesn't mean that they always will be, obviously. And obviously it didn't cross at positive 1 and negative 1 and positive 6 and negative 6 and you see what I mean? This is just a list of possibilities. Okay? All right. And again, I can see on the graph that the other two really are there. Alright, so let's try this one. Alright, we need a list. So my a sub naught is negative 6, factors of 6, 1 and 6, 2 and 3. My a sub n is 4, factors of 4 are 1, 4, 2, and 2. I don't list it twice. Okay, I've got to get my PQ list, so I'm going to start with 1. And I'm going to have 1 over 1, 1 over 4, 1 over 2. Then I'm going to have 6 over 1, 6 over 4, 6 over 2. And then I'm going to have 2 over 1, 2 over 4, 2 over 2. And then I'm going to have 3 over 1, 3 over 4, 3 over 2. Let's clean this up and get rid of repeaters and other junk. I have plus or minus 1, plus or minus 1/4, plus or minus 1/2, plus or minus 6. This reduces to plus or minus 3/2. This 6 over 2 reduces to plus or minus 3. 2 over 1 is plus or minus 2. 2/4 reduces to 1/2, and I already have it. 2 over 2 reduces to 1, and I already have it. 3 over 1 reduces to 3, and I already have it. I don't have 3/4, and I already have 3/2. So there's my possible rational zeros. Now you can see why I don't really want to try. That would give me 2, 4, 6, 8, 10, 12, 14, 16 division problems if I tested each one of these to see if they really were zeros, which is why we cheat a little bit. And I'm going to use my graph. Again, this thing could cross 4 times or 2 times or no times. The graph shows me it crosses twice. When I found the 0, it's negative 0.75. That's negative 3/4 if I turned it into a fraction. Now, don't panic on the fractions, guys. It's not that bad. If I put negative 3/4 in the hole, my 4th degree coefficient, my 3rd degree coefficient, my 2nd degree coefficient, my 1st degree coefficient, and my constant, 4 comes out. Use a calculator. Type in negative 3/4 times 4. It's going to come back as negative 3. The 4's cancel. Negative 1 eats negative 3, comes out negative 4, times negative 3/4, they cancel, and that comes out positive 3. 5 eats 3, comes out positive 8. I promise, type it in a calculator. 3/4, negative 3/4 times 8 is negative 6. That comes out negative 8. Times negative 3/4 comes back positive 6, which gives me a remainder of 0. And it better, or my graph is lying to me. So now that drops me down to a third degree function. So this will be 4x cubed minus 4x squared plus 8x minus 8. Now, the problem is it's still third degree, so I can't use my quadratic tools to get the remaining zeros. So I got to try another one. Negative 3/4 was 1. I got to find another one out of this list. And again, normally you would just pick and choose and try, but I'm going to use my graph. So I'm looking to see where that one is, and it's at positive 1. So now I'm going to put positive 1 in the hole. Okay, so I found another one, positive 1. There's got to be a total of 4 answers. Obviously, these are the only two that are going to be rational, or real for that matter. All right, but if I put positive 1, and I'm not going to divide the original, I'm going to divide the depressed one. So 4 comes out, times 1 brings back 4, comes out 0, brings back 0, comes out 8, brings back 8, comes out 0. That, my friends, has now dropped me from a third degree down to a second degree. And now I can use my quadratic techniques. What's left, I don't have to write the 0x, is 4x squared plus 8. Set that to 0 and solve it. Okay, because there's no first degree term, I can use the square root property. So I'm going to minus 8. I get 4x squared equals negative 8. Divide by 4, x squared equals negative 2, square root, x equals a positive I square roots of 2 and a negative I square roots of 2, because that negative comes out as I. So my 4 solutions are negative 3/4, positive 1, positive I square roots of 2, and negative I square roots of 2. 2 are real, right there. 2 are imaginary. Okay? And the only ones that are rational are those two. Okay? Alright, it says find a rational zero of the polynomial function and use it to find all zeros of the function. Hit pause, come back when you're ready. And hopefully you got 2. If I make my list, my a sub naught is 8, factors of 8, 1 and 8, 2 and 4. My a sub n is 3, factors of 3 are 1 and 3, so my possible PQs are 1 over 1, 1 over 3, 8 over 1, 8 over 3, 2 over 1, 2 over 3, 4 over 1, 4 over 3, plus or minus 1, plus or minus 1/3, plus or minus 8, plus or minus 8/3, plus or minus 2, plus or minus 2/3, plus or minus 4, plus or minus 4/3. There's my list. Normally we would just start picking and trying, but we're going to cheat a little bit and use our graph, and I can see 1 is at negative 0.333333, which is negative 1/3 repeating. So if I put that in the hole and divide it down to depress it down to a second degree, my third degree coefficient, my second degree, my first degree, my constant. 3 comes out, times negative 1/3 is negative 1. Negative 18 comes out, times negative 1/3 is positive 6. Positive 24 comes out, times negative 1/3 is negative 8, which gives me a remainder of 0, which now drops me down to a second degree function, which now 3x squared minus 18x plus 24 I can set to 0 and solve it. I'm going to factor this, and I notice I can factor out a 3, which would leave x squared minus 6x plus 8 equals 0. Keep the 3, factor the trino. Should be easy. A is 1, x and x. Factors of 8 that make 6 would be 2 and 4. C is positive, which means they both get the middle sign. 3, if I set to 0, doesn't make any sense. It's not a 0 factor, doesn't have an x in it. X minus 2 equals 0, x minus 4 equals 0. Add 2, x equals 2. We already got x equals negative 1/3, x equals 2, add 4, x equals 4. My 3 zeros are negative 1/3, 2, and 4. Which, yes, you could have just read from the graph, but there's the algebra to back it up. Alright, and you can see I found them on the calculator. Alright, you try this one. Hit pause, come back when you're ready. And hopefully you got number 2. Alright, my a sub naught is 4. Factors of 4, 1, 2, and 4. My a sub n is 1. Factors of 1 are 1. So 1 over 1, 2 over 1, 4 over 1. So plus or minus 1, plus or minus 2, plus or minus 4. Okay, I'm going to cheat and look at the graph. And I've got 1 at negative 5.64, blah, 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 blah. I got 1 at negative 2. I got these two are not rational. They're real, but they're not rational. But I got 1 that I can divide by. So I put negative 2 in the hole. So negative 2 is one of my rational zeros. And I can, again, I'm cheating a little bit. I can see if the other two aren't rational. But if I put negative 2 in the hole, third degree coefficient, second degree coefficient, first degree constant. 1 comes out, brings back negative 2, comes out 6, brings back negative 12, comes out 2, brings back negative 4, remainder 0, which is better, or my graph is lying to me. And that drops it down to a second degree. Now, if I try to factor this, I can't. There's no factors of 2 that make 6. So to find the other ones, I have to use my quadratic formula. So x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. That's going to be negative 6 plus or minus the square root of 36 minus 8 is 28 all over 2. If I break down 28 by 2 is 14, by 2 is 7, that gives me negative 6 plus or minus 2 square roots of 7 all over 2. Reduce by 2 and I get negative 3 plus or minus the square root of 7. So I have x equals negative 2, x equals negative 3 plus the square root of 7, and negative 3 minus the square root of 7. This one is rational, these two are irrational. Total of 3. Alright, so explain how to use the rational zero theorem to find all possible rational zeros, or rational roots of a polynomial. Well, you use the rational zero theorem to you make your PQ list, and then you guess and check the PQs. We cheat. We kind of look at our graph. Alright, then you divide until your polynomial is second degree. And then you either factor or do quadratic formula to find the remaining zeros. Alright, the linear factorization theorem. What the linear factorization theorem says is that if you have an nth degree function, then there are going to be n linear factors. They might not all be real, alright, but they can be factors. So look at this function. Okay, it's a 6th degree function. According to the linear factorization theorem, what that means is I should get 6. This should be able to factor into 6 linear factors. And it does. Don't worry about how right now. We'll worry about that later. But I promise this is what this factors into. Now, and I did this on purpose so that you could see the different kinds of factors. Notice how I kind of color-coded them. if I set these equal to 0, okay, and got x alone. So if I did x plus 3 equals 0, minus 3 minus 3, I would get x equals negative 3. 2x minus 1 equals 0, add 1, I get 2x equals 1, divide by 2, I get x equals 1/2. X plus the square root of 2 equals 0, minus square root of 2, minus square root of 2, I get x equals the negative square root of 2. So on and so forth. X minus the square root of 2 equals 0, add the square root of 2, add the square root of 2, x equals the square root of 2. These ones are kind of funny because you have to get everything. If I said x minus 4 plus 5i equal to 0, I would add 4. That would give me x plus 5i equals 4. Then I would minus 5i. And I get x equals 4 minus 5i. And then if I did this one, x minus 4 minus 5i equals 0, add 4. I get x minus 5i equals 4, add 5i, x equals 4 plus 5i. Okay, so do you see where I got all my zeros from? Okay, so I have the, oh, I guess I did all that. I set each one to 0. Alright, and then what they're going to ask you is the rational zeros. Sorry, I didn't realize I did that. So minus 3, x equals negative 3. Add 1, 2x equals 1. Divide by 2, x equals 1/2. Minus the square root of 2, minus the square root of 2, x equals a negative square root of 2. Add a square root of 2, add a square root of 2, I get x equals a positive square root of 2. Add 4, minus 5i, I'm doing two steps at once, I get x equals 4 minus 5i. Add 4, add 5i, I get x equals 4 plus 5i. Now, the rational zeros are numbers that can be written as fractions. So my rational zeros are negative 3 and 1/2. My irrational zeros are the ones that have radicals in it. So negative square root of 2 and positive square root of 2. And my imaginary ones are ones that have i's in them, obviously. 4 minus 5i and 4 plus 5i. Now, it wants to know which ones are real. The real ones are the rational and the irrational. So my real ones are negative 3, 1/2, negative square root of 2, positive square root of 2. And the non-reals are the ones with i's in them. Okay? So do you see how you go from a function to factors to zeros? Because we can also go backwards. We can start with zeros and then go back to factors and then multiply them together to get the function. Okay? We're going to be doing a little both of that. So, properties of roots of polynomial equations. It says if a polynomial equation is of degree n, then counting multiple roots separately, the equation has n roots. So if your degree is n, that's how many roots you have. Okay, you might have some that repeat, you might get doubles, you might have some that are rational, irrational, but if you have a degree n, then you're going to have n roots. The second thing is, if you have a complex root, then guaranteed, its conjugate is also a root. It's called the complex conjugate theorem. Okay, and the fundamental theorem of algebra says, if f of x is a polynomial of degree n, then the equation has at least one complex root. It actually says that if it's degree n, then you have n complex roots. Because you can even if I said x equals 3, I can write that as a complex number by saying 3 plus 0i. Okay? At any rate, you're going to be writing polynomials given the zeros. So like I said, we're going to be going backwards. They're going to give you the zeros. You're going to write them as x equals whatever they gave you. And you're going to turn them back into factors. Then you're going to set up your equation. Your equation is of some leading coefficient times all your factors. They're going to give you another point so that you can figure out the leading coefficient. So you're going to plug that in for x and y. You're going to put the y here, and all the x's in the factors are going to change. And then you're going to solve for a sub n. Then you plug a sub n in and simplify if you're asked. So it says, find an nth degree polynomial. So they're telling me this is degree 4, which means I need 4 zeros and 4 factors to multiply together. And they want me to write the function. Well, they want degree 4. This says these are the zeros that they gave me. Okay, so it says that x equals 3, that x equals 1/2, that x equals 3 plus 2i, and that x equals 3 minus 2i. What? I don't see that written up there. Okay, you got to remember the complex conjugate theorem that says if they give you a complex zero, then guaranteed its conjugate is also a factor. Alright, so now we're going to turn these into factors. So minus 3, that gives me x minus 3 equals 0. There's one factor. We don't want fractions, so instead of just subtracting 1/2, which you could do, I'm going to kill the fraction. So I'm going to multiply by 2, which gives me 2x equals 1. Then minus 1, I get 2x minus 1 equals 0. Minus 3, minus 2i, I get x minus 3 minus 2i equals 0. Minus 3, add 2i, I get x minus 3 plus 2i equals 0. So I wrote my zeros and then I turned them into factors. Now I'm going to set up my equation, which says f of x equals some leading coefficient that I don't know times all of my factors. X minus 3, 2x minus 1, x minus 3 minus 2i, x minus 3 plus 2i. Okay, so then it says plug in the x and y from the point given. See how they give me this f of 1 equals 32? What they're telling me is if I change x to 1, I will get 32 for y. So if I plug that in, I'm going to change this to 32, a sub n, and I'm going to change all of my x's to 1. So I have 1 minus 3, 2 times 1 minus 1, 1 minus 3 minus 2i, 1 minus 3 plus 2i. And I'm going to solve this for a sub n. So inside parentheses, I get negative 2. 2 minus 1 is 1. 1 minus 3 is negative 2 minus 2i. 1 minus 3 is negative 2 plus 2i. If I start multiplying these together, I get a sub n times negative 2 times, I'm going to go ahead and multiply these two together. I'm going to multiply these two together. This is going to be negative 2 times negative 2 is 4. Negative 2 times 2i is negative 4i. Negative 2i times negative 2 is positive 4i. Negative 2i times positive 2i is negative 4i squared. Okay. Clean it up. The i's cancel. This turns into negative 4 times negative 1, which turns into positive 4. So now I have 32 equals a sub n times negative 2 times 4 plus 4 is 8. So that gives me 32 equals negative 16 times a sub n. And to finally get a sub n alone, I'm going to divide by negative 16, and a sub n equals negative 2. So now that I know that, I'm going to plug it in right here, and I'll have my function. So my function is negative 2 times x minus 3 times 2x minus 1 times x minus 3 minus 2i times x minus 3 plus 2i. Now, there's my function. Now, if they want that in standard form, you're going to have to multiply all of that together. And I don't think that they're going to make you do that. Alright. Yes, they are. Never mind. Alright, so we're going to have to multiply all this together. Let's finish this off. Okay, so I'm going to do 2 at a time. So that's going to give me negative 2x plus 6 times 2x minus 1. That's going to be negative 4x squared, positive 2x, positive 12x, negative 6, clean it up, negative 4x squared plus 14x minus 6. Now, I got all these three done. I'm going to multiply these two together because they're conjugates and it'll kill the i's. And then when I'm done, I'll multiply those two together. So, over here, I'm going to have x times x is x squared. X times negative 3 is negative 3x. X times 2i is 2xi. I'm so not going to have room. Negative 3 times x is negative 3x. Negative 3 times negative 3 is positive 9. Negative 3 times 2i is negative 6i. Negative 2i times x is in the greeny blue thingies. Negative 2i times x, I'm going to have to come down here, is negative 2xi. Negative 2i times negative 3 is positive 6i. Negative 2i times positive 2i is negative 4i squared. So now, if we combine like terms, the i's should all cancel. Negative 2xi, positive 2xi, positive 6i, negative 6i. That's going to be negative 4 times negative 1, which is going to be positive 4. So that simplifies down to x squared minus 6x plus 13. And now if we multiply, hold on. Now if we multiply those together, I have negative 4x squared times x squared is negative 4x to the fourth. Negative 4x squared times negative 6x is positive 24x cubed. Negative 4x squared times 13 is 52, negative 52x squared. Next, 14x times x is 14x cubed. 14x times negative 6x is negative 84x squared. 14x times 13 is 182x. And negative 6 times x squared is negative 6x squared. Negative 6 times negative 6x is positive 36x. Negative 6 times positive 13 is negative 78. Combine like terms, and my final function is, come on. Negative 4x to the fourth, 24x cubed plus 14x cubed is 38x cubed, negative 52x squared, negative 84x squared, and negative 6x squared is negative 142x squared. And then we have 182 and 36, which gives me 218x minus 78. There is my function. Alright, you try this one, hit pause, come back when you're ready. And hopefully you got number 3. Alright, they want a fourth degree. They're telling me that x equals 3, x equals negative 1/3, x equals 1 plus 3i, which means x also equals 1 minus 3i. So if I write my function, I'm going to have f of x, I'm going to skip some steps here, equals x minus 3. Multiply by 3, add 1 is going to be 3x plus 1. X minus 1 minus 3i. X minus 1 plus 3i. And my a sub n. So then we use our ordered pair, and we have 144 equals a sub n. 1 minus 3. 3 times 1 plus 1. 1 minus 1 minus 3i, 1 minus 1 plus 3i. If I simplify this and clean it up a little bit, I got 144 equals a sub n times negative 2 times 4, those cancel, times negative 3i, those cancel, times positive 3i, which makes 144 equals a sub n times negative 8 times negative 9i squared. That's going to turn into a negative 1 times negative 9 makes a positive 9 times negative 8 times a sub n. So now I got 144 equals negative 72 a sub n. Divide by negative 72, and a sub n equals 2. Alright. So now, wait a second. So now that I've got a sub n equals 2, if I plug that in back here, I have, or back here I should say, I have my function is 2 times x minus 3 times 3x plus 1 times x minus 1 minus 3i times x minus 1 plus 3i. And if we multiply all that mess together, you should end up with this function. Okay? I'm going to do some of this. I'm going to do these two on the side here. So if I have x minus 1 minus 3i, x minus 1 plus 3i, that's going to give me x squared minus x plus 3xi minus x plus 1 minus 3i minus 3xi plus 3i minus 9i squared. The xi's cancel, the i's cancel, and I have x squared minus 2x plus 10. If I do these two, okay, so this becomes x squared minus 2x plus 10. These two, if I do this to the side, x minus 3 times 3x plus 1, 3x squared plus x minus 9x minus 3, that's 3x squared minus 8x minus 3 times this 2 makes 6x squared minus 16x minus 6. Alright. Multiply those together, and I have not the right answer. What's going on here? 6x to the 4th minus 12x cubed plus 60x squared minus 16x cubed. Something's wrong. Plus 32x squared minus 160x minus 6x squared plus 12x minus 60. That would give me 6x to the 4th minus 28x cubed plus 92x squared. Nope. 92 minus 6 is 86. Minus 86x squared. Minus 160 plus 12 is, I'm all messed up, 148x minus 60. Alright, I'm going to have to look at that because I'm not really sure. I've got my numbers right, my signs are screwed up, so I had to have messed up something up here not paying attention. Times 3 plus 1, right? Minus 1 minus 3i. All right, I will look back at that and figure out where we messed up. All right. So for some homework help, it says a popular model of carry-on luggage has a length that is 10 inches greater than its depth. Airline regulations require that the sum of the length, the width, and the depth cannot exceed 40 inches. These conditions, with the assumption that this sum is 40 inches, can be modeled by this function. Okay, and it says use function v to solve exercises 61 to 62. It says if the volume of the carry-on luggage is 2,000 cubic inches, determine two possibilities for its depth. What they're telling you is to change volume to 2,000. Okay, so if I type this function into y1 and 2,000 in for y2 and calculate an intersection point, now to get a good picture, notice what I had to change my window to. Okay, and I'm going to stretch it a little more because I think this is going to cross twice. I just think it's hidden. So I stretch it a little more and you can see there's my one answer, there's two answers, there's three answers. Now this answer doesn't make any sense because it's negative. So if we calculate those two, I get 7.8, because it said round to the nearest tenth, 7.8, or 10. 10. Okay, those are your two possibilities. And it says identify your answers 61 as points on the graph. Well, again, it was this point right here and this point right there, 7.8 and 10. Okay, so we already answered that. We are at homework, so we are done. Happy homeworking. I hope somebody can find out my answer, where I screwed up on that one. Let me know.